So now the question is when to share. So if you see, when does a node has to send its partial routing table? So we discussed that in distance vector routing, every node sends two columns to its immediate neighbors, right? So this information should be sent at some point of time. So the question is, when does a particular node send the partial routing table? So the answer for this is the table will be sent to its neighbors periodically and also when a change happens in the table. So when will the change happens in the table? When there is a change in the network, that is when a particular router is down or a particular link is having some problem or if there are many other cases. Okay. So the first thing is periodical update. So in periodical update, what actually happens? Generally, every node sends its routing table updates for every 30 seconds. Okay. So this period, that is whether it is 30 seconds or 60 seconds, depends upon the protocol which is using this distance vector routing protocol. Okay. So it may not be all the time 30 seconds. It depends upon the protocol we are going to use. So this is about periodic update. And the second thing is triggered update. The second type of update is triggered update. So triggered update means a node sends its two-column table only when there is a change in the routing table. See, in the previous scenario, this is not about the change in the routing table. This is a periodical update. Okay, the second strategy is only the routing table is shared only when there is change in the routing table. That is, the change in the routing table triggers a particular node to send the updated routing table to the all the neighborhood nodes. Okay, so when this updated routing table is sent to the other neighboring nodes, what changes will happen? Obviously, a particular node receives the table from the neighbor and it is going to change its own table. See, now A has received a particular value, A has received a particular table from node C. Now it is going to modify the table and then it compares its modified table with the old table and finally it will come to a particular conclusion of its new table. So a particular node detects, if a particular node detects some failure, let us say node, this is node A, okay, and this is node C. If node C detects a link in its neighborhood, okay, then it is going to update its routing table and it sends the same routing table update to the node A also. So this is what we are going to call it as triggered update. Okay. Now, so till now we have discussed about the distance vector routing. Okay, so in distance vector routing, what we did, we discussed a particular node is going to send its two column values to the all the neighboring nodes. Now let us now discuss about the problem with the distance vector routing. One of the most important problems when we are discussing about the distance vector routing algorithm is two node loop instability. So what is this problem? Two node loop instability. This is the problem if we employ the distance vector routing algorithm in our network. Okay. So let us now briefly discuss about what is this two node loop instability. Okay. So whenever our network uses this distance vector routing algorithm, the network is affected with some instability. Okay. So let us now see how the network will become unstable. Okay. How the distance vector routing algorithm makes the network to become unstable. Okay. Let us now see with an example. Okay. So initially, if you see, this condition is before failure. Okay, so this particular condition is before failure. Okay, let us now see. So if you see here, node X is connected to node A and node A is connected to node B. If you now see, the routing table for node A is, that is the first part. This first part tells that A is connected to X with a distance of 2 and the next hop is hyphen, I mean dash, because there is no other hop between A and X. Okay, so we can simply understand this part, right? So the first X means A is connected to X and the second one is the distance between A and X is 2 and the last one is there is no next hop. Then what about B? So now when B wants to go to X, okay, so what is the distance? So first of all, B has to go to A and then from A it has to go to X. That is the packet from B, it has to go to A and then from A to X. So B knows that its distance from B to A is 4 and A knows that its distance from A to X is 2. So what will be the final value of b to x? Obviously 4 plus 2, which is nothing but 6. Right? So what will be the next hop for B? The next hop for B, that is for B to reach X, it has to go through A. So this is the reason we have A here, right? So this is our normal thing. So let us say now, due to some reason, the link between A and X has failed. Okay. So when now the link between A and X has failed, what actually happens? So if you see here, now A has updated its routing table for reaching X as infinity. That is, it cannot reach X. That is, the distance is infinity. Now node A cannot reach X. Or that is the reason it has updated the table from 2, the value 2 to infinity. So in distance vector routing, what did we say? Whenever there is a change in the network or whenever there is a change in the links, automatically this node will send the update to now whom? It will send the update to B. Okay. So if A sends this update to B, then there is no problem. Okay. But what if B sends an update to A before A sends an update to B? Okay. So I hope you will. I hope you are going to understand this problem. Okay. So initially, if you see here, A, whenever it get disconnected with X, it marked with infinity. Okay. So let us stop here. Okay. Now, what I am going to tell at this moment of time, some periodic moment of time, now B is sending the update because of some periodic update also, the node is going to share its routing table, right? So now B is sending its update to A. So what B has sent its update to A? B is sending that B can reach X. Okay, B can reach X with a distance of 6. Okay, now the same update. Now, when B is sending this update to A, now what A thinks that okay, I am unable to reach X. Okay, but now B somehow is able to reach X, so that now A updates its routing table from 6, that is from B to X it is 6, right? But from B to A it is 4. So what is 10 plus 6 value? I mean, what is 6 plus 4 value? 10. Now A mistakenly thinks that now it can reach X through B because the next of value is now B here. If you see here, okay. So now what A is going to think? A can go to B and from B it can go to X with the distance of 10 units. Okay, but does A really go to X through B? Obviously, no. Okay, this is at one moment of time. For the next moment of time, again, now A is going to send its update. Okay, when A is going to send its update, already A can reach X with 10 units. Now, when it is sending the update to this one, now what B again it is going to update because A can reach to X with 10 units. So now B can reach to X through A with 10 plus 4 means 14 units. Okay. So when B receives the update from A, now it became 4. And again when again A receives the update from B, then it will be again adding this 10 plus again this 14 plus again for 18 and so on. Finally, what they are going to reach? They are going to reach the infinity value. That is, soon after they are updating their routing tables, A is also telling that it can go through B. B is telling that it can go through A. That is the packet. If it wants to go from A to X, always it go from A to B. And whenever it gets to B, it says that from B to A. So here they are going to loop out, right? So that is the packet is being looped between these two nodes only. So this type of problem is called two node loop instability. Okay, so this is the actual problem with the distance vector routing algorithm. So now let us now discuss about the solution for this particular problem. So the solution for these problems could be defining infinity, and then the second one is split horizon, and the third one is split horizon and Poisson reverse. So let us now see what is defining infinity. So this is the first and foremost solution. Here we wanted to redefine the infinity value to a smaller number. So if you see, initially it has reached from 6 to 10, some 10 to 14, some 14 to 18, 18 to 24, and so on. They are going up to infinity. So now, instead of going or reaching up to infinity, now we ourselves define the value of infinity. Let us say if the value crosses 100, okay, then we stop updating the table. Okay, so here we define a smaller number, let us say some 100. Okay, so Whenever now the system is going to share these updates, so when it gets this value 100, then it stops sharing because we defined the upper limit of this infinity value to be 100. Okay, but generally most implementations of these distance vector protocol, they define the distance of each node between 1 to 16. That is, whenever they are sending the updates, okay, so only one node, that is, let us say this is a node, only all the 16 nodes on the right side and all the 16 nodes on the left side, okay, that is, we can define infinity only up to going for 16 hop counts this side and 16 hop counts this side, okay. That is, the size of the network in each of these directions cannot exceed 15 hops. That is, it can reach only 15 hops. So if it crosses 16 hops, then it could not update all these values. That is, here, what is the main intention behind defining infinity? Means we can define our own number. Okay, we will define a smaller number. So whenever the distance metric reaches that particular number, then those nodes stop sending the updates to all those nodes. Okay, so this is about defining infinity. Now coming to the second thing called split horizon. So what is split horizon? So here, instead of flooding the table for each interface, here each node sends only a part of the table through the interface. See, if you see here, actually we are going to send the updates of the complete table, right? But here in the split horizon, what we are going to say is, we are going to send the part of the table through each and every interface. That is, let us say, if in this example, B thinks that, if you see here in this example, B thinks that the optimum route to reach X is via A. Okay, if you see, I'm going to clear these values, then it will be more. Okay, so in this diagram, if you see, node B, that is, this is node B. This node B thinks that the optimum route to reach X is via A, of course, because B is not directly connected to A, it has to go through A. But it actually does not need to advertise this information to A, right? So actually A know how to go from A to X, right? So B, there is no need for B to tell A how to reach X, right? So there is no need for B to advertise this information to A now, okay? Because it already got the information from A of how to reach X. So B can directly reach X through A, but there is no need for B to send the routing table update again to A, because when B is sending the routing table update to A, then only we are going for the counter infinity problem, right? If B is not going to send this update, obviously B will come to note that at particular point of time A cannot reach X, right? So this is how we are going to solve the problem of this two node loop instability with the help of split origin. Okay. The next kind of thing is split horizon with Poisson reverse. Okay, so actually the split horizon, that is when we are using the single split horizon, is having some drawback. So we know that distance vector protocol is going to use a timer. Okay, so if we within a amount of time, if there is no news about any particular route, the node is going to delete the route from its table. Okay, so if you see, if in a particular point of time, if this node do not get any information about the route, what it is going to do, the node is going to delete the route from its table. Okay, so if in this example, if node B do not get any information about the node X from A, then what it will do, the node B is going to eliminate the route to X from its advertisement to A, right? So now node A, for node A there is no, I mean for node A there is no chance that, due to split horizon strategy, actually due to split horizon strategy, B is not sending the update to A, right? In order to avoid the two node loop instability, we are following split horizon, and due to split horizon strategy, now B is not sending any update to A. Okay, so for this reason, what we are going to do, we are going to add this split horizon strategy with the Poisson reverse strategy. Okay, now what it will do, now node B will advertise the value of X, but if the source information is A, it can replace the distance with infinity as a warning that do not use this value, because what value I get from you is from you. Okay, so if you see, so what I mean to say is we are adding this split origin with the poisson reverse. Poisson reverse means we will advertise its value to A, but what it will say along with that, please do not use the value which I am sending you, because I got this information from whom? A. So I got information from you only, but again this information I am sending to you. So please do not use this information. Okay. So we are getting the problem only if A is using the information from B. So if B can say A that please do not use this information because I got this information from you, then there is a chance for A not to go to infinity problem. So from A, B will not go to count to infinity problem. Okay. So this is how we are going to provide solution for this count to infinity problem in when we are employing two nodes. Okay. The next thing is three node instability. Same thing. So if you see here again, when we have three nodes connected to, I mean, let us say they wanted to send information to before failure. This now we can come to know what is this one, what is this one, and what is this one, right? So C can reach X via A with cost 5. B can reach X via A with cost 6. A can reach X with cost 2 without any intermediate hop, right? Now, when A is sending the route to B and C, if you see here, now A is going to send the route to B and route to C, telling that now I missed the link, that is the link between A and X has been, I mean, is a failure. So A కి X కి మధ్య లింక్ తెగిపోయింది అన్న విషయాన్ని B కి C కి పంపించింది. ఓకే. సో డ్యూ టు నెట్వర్క్ ప్రాబ్లం C కి ఆ ప్యాకెట్ వెళ్ళలేదు, కానీ ఓన్లీ B కి మాత్రమే వెళ్ళింది. ఓకేనా. సో ఇప్పుడు A ఎలాగూ ఇన్ఫినిటీ అని అనుకుంది, ఎందుకు A నుంచి X కి ఇన్ఫర్మేషన్ వెళ్ళదు కదా, వెళ్ళలేదు, లింక్ ప్రాబ్లం అయింది కాబట్టి ఇట్ హ్యాస్ అప్డేటెడ్ దిస్ డిస్టెన్స్ కి ఇన్ఫినిటీ. సో ఇదే ప్యాకెట్ డీకి కూడా వెళ్ళింది కాబట్టి ఇది అప్డేట్ చేసుకుంది, కానీ సికి ప్యాకెట్ వెళ్ళిందా, డ్యూ టు నెట్వర్క్ ప్రాబ్లం ప్యాకెట్ వెళ్ళలేదు. సో ఆబ్వియస్లీ దీని టేబుల్ ఇది అప్డేట్ చేసుకోదు. బట్ పీరియాడిక్ టైం ప్రకారం ఏం చేస్తుంది సి, దీని అప్డేట్ ఏకి పంపిస్తుంది, దీని అప్డేట్ బికి కూడా పంపిస్తుంది. సో ఎప్పుడైతే ఈ అప్డేట్ ఏకి బికి పంపించిందో ఇక్కడ ఏం చేసేది చూడండి. సో ఇన్ఫినిటీ వాల్యూ కాస్త మళ్ళీ ఇక్కడ బి వాల్యూ ఏమైపోయింది, 8 కింద మారిపోయింది. అంటే ఏం చెప్తుంది ఇక్కడ సి, నా దగ్గర నుంచి ఎక్స్ కి 5 డిస్టెన్స్ తో వెళ్ళొచ్చు అని బీకి చెప్పింది, అండ్ బి నుంచి సికి డిస్టెన్స్ ఎంత 3. సో 5 + 3 ఎంత 8. సో ఇప్పుడు బి ఏమనుకుంటుంది, ఓకే నేను సి ద్వారా నా దగ్గర నుంచి ఎక్స్ కి 8 యూనిట్స్ డిస్టెన్స్ తో నేను వెళ్ళొచ్చు అని చెప్తుంది. సో ఇదే అప్డేట్ ని ఇదేం చేస్తుంది, ఏకి పంపిస్తుంది. సో ఏకి ఎప్పుడైతే పంపించిందో బి నుంచి ఎక్స్ కి 8 యూనిట్స్ డిస్టెన్స్ వెళ్తే బి నుంచి ఏకి 4 ఉంది కదా. సో ఏ ఏం చేస్తుంది, ఈ 8 కి 4 ని కలిపి ఓకే ఇప్పుడు నా దగ్గర నుంచి నేను ఎక్స్ కి 12 యూనిట్స్ డిస్టెన్స్ లో వెళ్ళిపోవచ్చు మాట అనుకుంటుంది. బట్ యాక్చువల్గా ఈ లింక్ ఉందా, దిస్ లింక్ ఈస్ నాట్ దేర్. సో దిస్ ఈస్ హౌ వీ హ్యావ్ 3 నోడ్ ఇన్స్టెబిలిటీ ప్రాబ్లం. సో ఈ విధంగా కౌంట్ టు ఇన్ఫినిటీ ప్రాబ్లం అనేది మనకి డిస్టెన్స్ వెక్టర్ రౌటింగ్ అల్గోరిథం లో మెయిన్ గా వస్తుంది. ఓకే.